Welcome. My name is Andres Castillo, and today we'll be discussing fog computing in a manufacturing environment, ICTN 6875 Emerging Technologies. So today, we'll be discussing the following, the evolution of cloud computing and the industrial Internet of Things. We'll define fog computing and the benefits of fog computing architecture, challenges to the design, and we'll have some, in conclusion, some additional resources. To begin, we have the evolution of cloud computing and the industrial Internet of Things. So in order to understand fog computing, we must first understand how the platform is an evolution of cloud computing and the Internet of Things. So what is cloud computing? Cloud computing is a configuration of remote hosted servers storing, processing, and collecting data over the internet. Some benefits of cloud computing include scalability and cost savings. So just as an example, we have a global manufacturing company that decides to deploy an application worldwide. The data collected for this application will be consolidated and archived for analysis and reporting information, which will affect business decisions and the manufacturing production for the plant, for several plants. So if each plant were responsible for purchasing software, hardware, copy of the application, database licensing and maintenance, and all the necessary, all these are necessary for deploying the application, there's a high potential for high overhead costs and inconsistency of data output. Each site would be independent of each other. And so application configuration, system configuration, support models, disaster recovery plans, and support resources would be multiplied across the domain. So as an alternative, the corporation determines a data center, which can be configured through internal or external sources, is needed to centrally house the application and the database servers. As data is collected and transmitted from the plant over the private wide area network to the data center, it can provide a consolidated view for analysis of multiple locations in a matter of minutes. Maintenance systems, support, and application support can all be centrally managed, and with a centralized configuration, it provides cost savings across the whole company. So deploying the application client is also centrally managed and can provides the ability to rapidly distribute the application to multiple endpoints simultaneously. Not only is the potential for cost savings in licensing and support and maintenance, but application availability and disaster recovery plans are now centrally managed as well. So examples of cloud computing in manufacturing. So in a pharmaceutical plant, there are several applications collecting data from chemical lab instruments connected to PCs or directly connected to the network, ensuring the quality and efficacy of the product. The collected data is recorded and used for producing records of batch information, adherence to quality standards, and for evidence to the Food and Drug Administration that it was documented, consistent, and safe. The data is transmitted across the WAN to a centralized repository or a data center somewhere off-site, and which is then analyzed and archived, used for reporting and for oversight. So management from across the globe now has access to all this live data from multiple locations. Another example, more common to most manufacturing facilities, relates to IIoT devices. So what is IIoT? It is Industrial Internet of Things. So the original term, Internet of Things, refers to any device other than the typical laptop or PC connected to the internet. So for example, you have cell phones, cars, household appliances, OnStar, and anything else that can communicate with the internet. Manufacturing plants have been around for many decades, so some still maintain equipment originally purchased, 20, 30, 10 years ago, so decades ago. And within the production infrastructure are devices used to monitor, manage, and control production machinery, monitor environmental controls, record production information, and identify potential issues in production machinery. So these devices have gradually migrated onto the local area network, and now rather than individuals walking to each point and manually recording data, data now flows to a centralized data historian. Multiple endpoints transmit the information over the LAN, and in some cases over the WAN. Devices can either be hardwired or use wireless connections to the network. So as manufacturing processes improve, we see upgrades from legacy hardware to modern equipment pre-configured for network connections, working in conjunction with application hardware and software for centralized data collection. A term now describing the newly connected devices are called industrial Internet of Things. So it means that those devices are just geared towards the manufacturing processes and controls. Information is collected from these programmable logic controllers, or PLCs, from sensors and through the supervisory controlled data acquisition system, or SCADA, these are used to maintain the sensors, actuators, make adjustments where necessary, environmental sensors, and so on. So within the diagram, you can see the various levels of IoT architecture. At the bottom level, you can see the endpoint devices that are moving up to the zone gateways. And within these zone gateways, these can be just like a regular switch, a dumb switch, or non-managed switch. And this allows the data to communicate to devices that are within that little network much more quickly. But these are not intelligent switches and do not have the ability to make any processing. So as we continue up the ladder and we look into the zone gateways and then move on to the enterprise network and then the application and then the wide area network where the application would be at a global scale. So this design provides a general overview of cloud computing and the industrial Internet of Things. So now that we have a basic understanding of cloud computing and IoT, we can move forward to fog computing. So a couple of years ago, there were a group of businesses who got together and noticed that there was a the rapid growth of the Internet of Things, and so they decided to get together and create a open fog consortium. So this was created back in 2015 by founding members Cisco, Dell, Intel, Microsoft, ARM, and Princeton University. It was formed to create a standardized IoT networking format to allow endpoints to communicate in a secure and private architecture. So these companies had the foresight to see the rapidly expanding growth and data transmission over the internet, which is usually happening in an inefficient format and would require a standardized computing structure. It is projected that literally billions of devices from around the globe will eventually connect to the internet. This standardization is working towards reducing internet traffic, ensuring security, and accelerating IoT communications. So since its inception, several more corporations from various industries and around the world and companies around the world have joined and are now working towards the goal of standardized architecture. Fog computing. So as stated previously, fog computing evolved from the concept of cloud computing and is used to enhance, not replace, the architecture. So the term fog computing is generally associated with Cisco and refers to bringing the cloud down to the ground level. So in essence, it's bringing the device, the intelligence closer to the device that's initiating the information. So an overview of some of the basic concepts. There was an article written by Jacob Pizon and Jerzy Limsky. In that article, they wrote within the applied computer science, it says fog computing is a highly virtualized platform that provides compute, storage, and networking services between end devices and the traditional cloud computing data centers, typically but not exclusively located at the edge of the network. So normally a network edge switch or an unmanaged switch would be at this level, and as we noticed earlier, and it wouldn't have the capability to perform any intelligence. It's like a traffic cop. It just takes the information and directs it to another location. So as far as addressing the need with fog computing, the article further discusses how some of the data transmitted from the device may not be necessary for the data collector at the other end of the hierarchy. So reducing traffic by removing packets of extraneous information can greatly reduce bandwidth utilization. And so as transactions occur, the fog device closest to the sensor begins the process of analyzing data and determining which packets will proceed to the next level. So this happens in an extremely fast method, as in it happens in milliseconds and subseconds. So depending on the requirement, I in my own personal experience, have seen some devices that do on average 10, 20, 30 collections per second, and depending on the network configuration, can be affected by latency. So latency is the time interval between the data that was initiated and when it was received. So data transmission through several layers of network devices has the potential to drop a packet or two due to latency. And if there was a switch that was down and routing compensated with a redundant path, potentially a gap would be created in the data historian with several seconds of or even up to a minute of lost data. So because the fog architecture initiates computing right after the device, so if you're looking at the diagram, you'll see that it has fog devices. Here's the device here at the endpoint, and then right after that, you can get to a node or fog computing device, and that information can get processed fairly quickly. So in another article written in the Journal of Manufacturing Systems, the authors state, as opposed to cloud computing, computationally intensive workloads, such as training large data sets and visualizing data analytics, are conducted in fog computing at locations where large volumes of data are collected and stored instead of centralized cloud storage. So in other words, in manufacturing on the lines, you have various endpoints, and those endpoints initiate information based on either whatever the motor functions are, or open closes, the temperatures, so various data collections that occur around the manufacturing process and machinery. And then decisions have to be made very rapidly as to whether the environment needs to change, or the doors need to stay open or closed, or just any number of things. And so those have to be processed very quickly. And if it takes time to go across the network and then come back, though it may take seconds, some of those decisions need to be made within milliseconds, and I believe this is one of the solutions that within fog computing that would allow that to happen. So going back to a practical application, in production, if a packet is dropped, it could potentially show a gap in the data collection, and every gap has to be investigated and determined whether the cause is of concern or not, and if there needs to be a corrective action which needs to be initiated. So when you're going through the process of manufacturing and the information is being analyzed, and then all of a sudden they start to see a gap, That causes questions, concerns, especially within a pharmaceutical industry. Everything has to be identified, justified, qualified. So if you have any type of gap, it can cause great concern because now you're dealing with medicines that affect people's lives. So control decisions are made from the data collected within the manufacturing line, and it could determine whether there's a potential problem with the line or sound an alarm or just stop production, which could help reduce the loss of product. Data computation at the earliest level allows automation to react in a more efficient manner. So here we have a Cisco diagram of multi-service field area networks. And within the diagram, you can see the integration of fog devices as they are, as compared to the previous diagram of cloud computing. There are these similarities where you have the various levels, data collection, and then the SCADA and HMIs and collectors, the historian. But with these, you have the level of the Cisco devices, which are right after the endpoints. And what we have here is a Cisco IR500 and then the WiMAX Wi-Fi. So that gives you some additional information. These two pieces of networking and computing equipment reveal that the incorporation of both wired and wireless configurations are communicated through these fog devices, and just reveals the versatility of collecting devices. Now, I'm not trying to promote Cisco here, but they have been the front runners in establishing fog devices and a fog configuration so that it can be implemented in various areas. And an important piece to also consider is that you have legacy manufacturing equipment, and you have inconsistency with some vendors. So these fog devices also have to have the ability to create or to connect with devices from various connection points like RS-232 or RJ45. So basically serial or network connections. So to have devices such as these would allow a manufacturing company to begin the process or installation for fog devices earlier rather than later because of their adaptability. The diagram also reveals the complexity for data traffic to travel from the initiator to the data historian. So basically, you can see that it's pretty complex. It goes through various levels. That information finally gets to a point and then lands. So latencies, if you have maybe the PC, the historian that's collecting the data, if it's getting a patch update, or if it is going through the process, through somebody may be on it doing something else, and it causes the processing to be overloaded, that could also drop. So there's a lot of interferences that can occur. So some of the device examples that would be used for collecting the data, just some examples that are out there. So you have a picture of a SCADA, which is the supervisory control and data acquisition, and this is the type of system that would incorporate other PLCs and the HMI, which is the interface allowing technicians to monitor and manage all the endpoints and understand what's happening within the entire system. So here is just a tablet that has the ability to also monitor and manage using some sort of HMI interface. So the growth of the IoT and IIoT devices is expanding and at a tremendous rate. and under the current architecture has the potential to overcrowd network bandwidth with both useful and unnecessary information. So the increased number of devices will produce latency issues, and when you're when you're seeing these, you can see that there would be gaps that could be created, but that would be with the cloud model alone. So as with all the other technology, there's always something newer, faster, and more efficient, and those are developed and constantly to meet with the challenges presented. So there is some terminology comparisons and some comparisons that are out there. So as a side note, some folks will use edge computing and use it as the same term as fog computing and kind of interchange them. The two are similar in the concept of computing closer to the originator, but they have differing solutions. The fog architecture puts the computing power on a network device, where the data is processed and returned rather quickly, and then the edge computing puts the computing power on an appliance, such as programmable automation controller. So a device that is more of a piece of hardware as opposed to a network switch. There are differing opinions on how each would process the data, but just like anything else, you have opinions, and somebody may like Windows OS and the other person may like Linux. Either way, they both take the intelligence and put it closer to the end device. So in an article written by Margaret Rouse, she identified a list of pros and cons to fog computing. So as far as benefits or pros, you have reduction in the amount of data transmitted to the cloud. You also conserve bandwidth. You have improved response time, improved security, and it supports mobility and reduces latency. So when you reduce the amount of traffic after the fog device going up to the historian, or consolidated it, it transmits and goes to the historian, and it can be collected in a much more efficient manner. Whereas the information initiated from the endpoint device going to the fog, basically computer, it can then create more efficient responses to the motor functions or the environmental needs, or the basically anything that's happening at the level of the manufacturing line or the manufacturing motor, and allow the fog device to respond in a more efficient manner. So some of the challenges are the physical virtual location is right next to the device, and it takes away from the anytime, anywhere, and any data benefit of the cloud. So essentially you have individuals who are wanting to understand what's happening at a particular location or even on a particular line, and within this configuration with fog computing, they have they don't have the same access as they would in cloud computing, because that would be a data center as opposed to the manufacturing line. So some of the security issues, you have possible IP address spoofing, man-in-the-middle attacks. You have some potential privacy issues, availability, cost of fog equipment, the hardware, trust and authentication issues, and wireless network security concerns. So these are all things that I know that the consortium is reviewing and going through and trying to adapt a much more secure and efficient manner for the data collection. So, in conclusion, we reviewed the cloud computing and the industrial Internet of Things. We talked about fog computing, what it is, the architecture, the benefits and the challenges, and we gave some examples of manufacturing with fog computing design. So I hope you've enjoyed this presentation and learned a little bit more about fog computing. And at the end, I've also given some references and some additional locations for some information that you can review for discussion. Thank you.